Hello, my name is Sarah Kroeker. I'm presenting for the CSM Virtual Research Showcase going live on May 8th, 2020. This research was done at Fresno State in our physics department's XRF lab under Dr. Mihai Garase. Today I'll be discussing how we make measurements of the X-ray attenuation coefficients for two different materials that we use in our bone lead concentration studies. So here's a quick outline of what I'm going to talk about today. I'll give you a healthy background on what XRF is and why we want to use that to measure lead concentration in bone. Then I'll discuss how we use an X-ray tube microbeam in this OGIP geometry to measure those lead concentrations. We'll also talk about how we do these soft tissue linear attenuation measurements of our phantoms. We'll give you the results of those linear attenuation measurements and compare them to the NIST XCOM database, which is essentially the gold standard for these measurements. So first we'll go into the background behind XRF, which is X-ray fluorescence, and this is a result of the photoelectric effect. So essentially you have in step one, a primary X-ray photon coming in, kicking out an electron from the K shell. And then in step two, you have an electron from a higher shell or a shell with a lower binding energy dropping down to fill in this hole. And in this picture, you have that coming from both the L or the M shell. They're just showing you two different options. In order for that to happen, those electrons must lose energy to drop down. And they do that by releasing a photon, which we refer to as X-ray fluorescence radiation. These photons are of a very specific energy, and we can use them to identify different elements in a sample. Now, I'll just briefly touch on the differences between K and L shell XRF for the sake of time. This is an example of the atomic energy diagram of lead, and so you can see all of the K shell XRF are the blue lines and the L shell are the red lines. So this is all of these subshells, and you can see the binding energy for the K shell is much greater than the binding energy for the L shell. So it requires a lot less energy to kick off a K shell electron than it does for an L shell electron. And that is an obvious benefit for L shell and why we want to use it in our research. The cons of that, however, are that because you have lower energy photons and lower intensity, there's a lot of issues with doing this calibration that is more streamlined and easier to do in a K shell XRF. But the cons of K shell XRF are that you have to use a radioactive source and a germanium detector, and so this is harder to do clinically. You have like a big bulky system that you can't just carry around and go to like a remote area if you want to do a population survey or easily implement into a clinic. We're interested in using L shell XRF to detect lead because it is well known to be a very toxic element to humans and living things. This graphic from the Arizona Department of Health Services is just giving you some broad examples of this. Even though in America we've reduced a lot of our exposure to lead in the previous common sources such as paint in older homes or in glazed pottery and things like that, it still is a danger in other places where you have mining or different construction activities going on, maybe in countries that don't have as strong regulations. And even a very small amount of lead is shown to drops in IQ or development. So it's very important to be able to survey a large amount of population or people in a lot of different areas to figure out what kind of lead levels do they have, and is that going to be causing some health effect that we can hopefully prevent. Here are some examples of how they've used KXRF to find lead concentration measurements. On the left, this is a device they use to measure the lead concentration in paint. Again, this uses KXRF, and I believe it uses some sort of radioactive source, but this isn't something that you can just go and point at a person and figure out what their lead concentration is. This is paint, it's right on the surface. We are more interested in finding it in the bone because the bone is actually a better indicator of a long-term occupational or environmental exposure. And that's what they're doing over here in this picture. They are using KXRF to measure the lead concentration in the bone. But again, this is your system setup. This is something that wouldn't be incredibly portable if you wanted to walk around and hold it. as much as this device is. So the idea with L-shell XRF is we could hopefully make something that is a lot more portable to use, and also would have less dose to the patient because your X-ray photons are going to be of lower energies. So on the left side, we have a schematic for our experimental setup. We have the beam exiting number 1, and it just grazes the interface between a bone phantom and a soft tissue phantom. We dope these bone phantoms with different concentrations of lead, and we see what XRF spectra comes out, and we collect that in number 3, which is the detector here. We call this the optimal grazing incidence position because we actually move this bone phantom and its soft tissue on a stage across the beam in 0.5 millimeter steps until the spectra we take shows a maximum for the strontium K alpha peak height. We use strontium because it coincidentally is in high concentrations in our bone samples, and this can help us determine where we should best position everything to then take our lead LXRF measurements. And so this is a picture of what it looks like in real life. This phantom represents the 75 ppm lead doped bone phantom with a POM or polyoxymethylene soft tissue phantom. Here's an example of what the spectrum might look like for this. As you can see, the strontium lines, which are number 1, 4, 5, are a little bit higher than our lead lines down here, which are in this tiny red box and blown up in the upper right-hand corner. So that's why we use them to figure out the best position. We take the spectra and then we will fit these L alpha and L beta peaks. To calibrate, we can then determine the lead concentration by plotting the lead peak counts per known bone phantom lead concentration. And that's an example in these 2 plots here. However, these calibration lines are specific to the different thicknesses and the materials of the soft tissue phantoms that we use. So if we want to use this on a person later where we don't necessarily know that information, we have to create some sort of calibration. So part of how we do this calibration is finding the X-ray linear attenuation coefficient of the different soft tissues that we use at their different energies and thicknesses. And so essentially, your attenuation coefficient tells you how well does this material absorb or scatter photons of different energies. So if you let n equal just the photons that are transmitted, and naught is going to be all the photons that originally come out of the X-ray beam, we use this equation to solve for mu, this exponential decay for each thickness of the tissue and at each energy. And so then once we know this attenuation coefficient, we can also figure out how well these materials simulate real life tissues as well. How we do that is in this schematic here. You have the beam, which comes out of our pixel collimator and our X-ray tube, and strikes our different samples that we have. We only collect what is transmitted through here, and we'll hopefully only collect what is transmitted, and that's how we find our N and N naught, and then we plug in the thickness that we measure of the sample. And so finally, we have our results. Here we have plotted the linear attenuation coefficient on the y-axis in inverse millimeters. On the x-axis, we have our photon energy in keV. The first plot is for a sample of pure aluminum, which we don't use as a soft tissue phantom, but we use it more for quality control. We see that it matches the XCOM data very well, so that is great. Over here, we have the measurement for polyoxymethylene, and we see that this fits the XCOM data for skin fairly well, and not so much for the chemical formula of POM, or polyoxymethylene. And we also see that our endpoints, we tend to have larger error bars, and this could be because we have much less photons coming out of our X-ray tube at those extreme endpoints. Most of our photons are around this 20 keV range. Additionally, we have our polyester resin, which doesn't fit the XCOM data for either skin or for a lot of these common resin formulas that we've looked through the literature. The particular formula for the resin we purchased is not available due to trade secret, so we simply just won't be using this soft tissue phantom. And over here we have paraffin wax, which very well matches adipose tissue for the energies that we're interested in. It starts to deviate at these endpoints here, but for what we're using, this should fit very well. And that wraps up our talk for today. Here's a shout out to our past and current undergraduate students also working in the lab, as well as our financial support from the College of Science Mathematics, as well as the National Institute of General Medical Sciences of the NIH. Thank you for listening.